It all begins when the lava hits the sea.
You can see the lavas having moved down from the volcano up here, sometimes in tubes, mostly in tubes. Now we're beginning to see it come out and go into the water and form the very newest bit of the island chain of Hawaii. As this lava hits the seawater, of course, it really chills very, very fast. And a very wonderful thing happens. They actually trap in, they record the Earth's magnetic field.
As they solidify and cool, these volcanic rocks are preserving a record of today's magnetic field. But the volcanoes of Hawaii have been erupting on and off for millions of years, building up the islands. Every layer of lava contains a record of the magnetic field at the time of that eruption. So the Hawaiian archipelago is a hidden chronicle of the Earth's magnetism stretching back 5.5 million years. That record shows there have been many fluctuations in the field's strength, but it contains something else of great significance. When lava cools, as with pottery, magnetic regions form within it. Acting like microscopic compass needles, they record not only how strong the field is, but also in what direction it is pointing. Today, the Earth's magnetic field runs from south to north, which is why compass needles point toward the North Pole, and recent lava flows record a field pointing north. But 50 years ago, when scientists measured the magnetism trapped in older lava samples, they made a startling discovery. The microscopic magnets within the lava were all pointing south.
When we go back about 700,000 years, we find an incredible phenomenon. Suddenly, the rocks are magnetized backwards. Instead of them being magnetized to the north, like today's field, they're magnetized to the south.
It seemed that prior to 780,000 years ago, Hawaiian lava must have cooled within a global magnetic field that was running to the south and away from the north, exactly the reverse of today. The bizarre implication was that at some point, the entire global magnetic field had done a sudden 180-degree flip, completely reversing direction.
It was hard for people to accept. They did not like the idea that the field reversed. It took about 50 years to convince people of this. But eventually, that was established, and really by work on this island, because if you keep on going down, you would find that after about another couple of 100,000 years, then it changes again, and you see this sequence going on.
And as they examined samples from older and older lava, scientists found more and more reversals. On average, one every 200,000 years.
And so by the time people had done that, it was pretty obvious that the field did indeed reverse.
But if the field has reversed so often in the past, it must surely do so again in the future.
That the Earth's magnetic field reverses is an extraordinary phenomenon. But this reversal process is quite common. The last reversal was, 780,000 years ago. Before that, there was one about 200,000. Before that, again, actually less than 200. So in a sense, we are a bit overdue for a reversal.
So is this why the field is growing weaker today? Could it be getting ready to flip? Scientists needed to discover whether there was a link between changes in the strength of the magnetic field and changes in its direction.
It was a very intriguing problem, something that was screaming out for an answer, And computers were becoming powerful enough to actually solve a full set of equations that describe convection in the core of the Earth and how that motion generates a magnetic field.
In the 1990s, physicist Gary Glotzmeyer decided to embark on a very ambitious experiment. He put all the essential facts that scientists had learned about the Earth's molten core into a computer model, dozens of equations describing its dimensions, temperature, viscosity, and so forth. Then he let the model run to see how the magnetic field would evolve over hundreds of thousands of years of simulated time.
It's important to understand just how long these simulations take. Each time the computer solves the equations, it advances the whole solution one time step. And the time step is typically 10 days. And within 10 days, things don't change much, which means you have to do many, many solutions. You have to solve it millions of times, tens of millions of times, in order to be able to simulate hundreds of thousands of years, which is what we needed. One case may take 6 months of running on the fastest computers in the world. I was using supercomputers from the Department of Energy, from NASA, and the National Science Foundation, and no matter where I was, the first thing I do is make sure the computers didn't crash. So it was something I did every day, 7 days a week, for over 4 years. And I remember there was a period of time, I believe it was in the fall, and I was traveling to other universities and giving talks, and after a number of weeks I came back and decided, well, now I need to look at the details of the magnetic field, and realized that it was in the reverse polarity. It already had reverse. This is something I didn't expect. So then I looked at many snapshots during the time I was gone and realized that the field did indeed reverse spontaneously. This is the first time it happened. We were very anxious to write about it. It was really exciting.
And as the experiment continued, so did the reversals, every 100,000 years or so of simulated time. And crucially, each time the field reversed, the process began the same way.
What's interesting is whenever it has reversed its polarity, its direction, that happened when the magnetic intensity was very weak. So it was decreasing, decreasing. Finally, when it was the dipole part of the field was very weak, then the field reversed.
Here was the evidence that what we are seeing today, a loss of field strength, is indeed linked to the onset of reversals. What's more, Gary could see why reversals are heralded by a weakening field.
Now this movie will show part of a simulation that spans magnetic field reversal. What you see here, blue represents inward directed magnetic field, the gold represents outward directed magnetic field.
In Gary's model, reversals seem to start with the appearance of islands of blue in the gold, and vice versa. These are magnetic anomalies, regions of the core where the field is already flowing the wrong way. As they grow, these patches where the field is reversed start to cancel out the main field, making it weaker and more liable to flip.
You see, as the time goes on, the field becomes more and more complicated, and then you get an anomaly growing in the northern hemisphere where the magnetic field now is going out. There's a reversal. Now the magnetic field is outward in the northern hemisphere and inward in the southern hemisphere.
So now the burning question is what's happening in Gary's model reflected in the real Earth? Is the 300-year decline in our field, which the pottery reveals, the work of magnetic anomalies brewing deep in the core beneath our feet? If so, then a reversal really could be in the cards.
If the north isn't true, will I lose my way to you?
Amazingly, there are detailed records that cover exactly this 300-year period. the logbooks of Her Majesty's Navy. For as geophysicist Jeremy Bloxham has discovered, 18th and 19th century sailors were obsessed with the magnetic field.
Back in the days of James Cook, when he was doing his voyages of exploration, a compass was the primary means of navigation. However, a compass needle doesn't point at true north, at the real geographical North Pole. Instead, it points at magnetic north.
For sailors, knowing the difference between true north and magnetic north was a matter of life and death. But as they were well aware, magnetic north keeps moving, wandering about near the pole as the field gradually changes. So navigators needed to measure the difference between magnetic north and true north, the angle of variation. They did this by comparing their compass bearing to an astronomical calculation of true north.
The trick was to find true north, and they could do this by looking at the sun at noon when it's highest in the sky, alternatively by looking at the angle the sun made at sunrise or sunset. Here on the 8th of June 1770 we have a magnetic variation of 4 degrees and 53 minutes east.
Thousands of these observations, together with early measures of the local strength of the field, have enabled Jeremy to reconstruct the ebb and flow of the Earth's magnetism over the past 3 centuries. And it's what this reveals about one region in particular that's significant.
We've seen very abrupt changes in the Earth's magnetic field beneath the South Atlantic Ocean.
Beneath the South Atlantic, Jeremy has found clear evidence for a region of magnetic anomalies, places where the field has already started to reverse. And these anomalies are growing.
As we get into the beginning of the 20th century, we see the emergence of a new patch of reverse flux, a region where the field lines, instead of coming out of the core, are looping back into the core. And that patch then drifts towards the west, hooking up with this other patch of reverse flux to create a large region, what we call the South Atlantic anomaly, where the field is about 30% weaker. And that patch has grown substantially during the last 100 years in particular. So one question we're all asking ourselves at the moment is the Earth's magnetic field about to flip?
In a region of the core 2,000 miles beneath the South Atlantic, the magnetic currents have reversed direction, canceling out the main field, causing its strength to decline. If things continue like this, then we could experience a magnetic phenomenon the Earth has not seen for 780,000 years. A complete flip of the entire global field.
There's really no question about whether the Earth's magnetic field will reverse again. The question is not if that's going to happen, it's when that's going to happen.
Actually, in the last few hundred years, the intensity of the magnetic field on the Earth has been decreasing, which is an indication that maybe we're in for a reversal. The average time between reversals is on the order of a few 100,000 years. We're actually sort of due for one.
No one has ever experienced a magnetic reversal. If this is really the beginning of a flip, what exactly will happen next? One man who may know is geologist Rob Coe. For 25 years, he's been coming to Steens Mountain in Oregon, a vast heap of hundreds of ancient lava flows.
"16 million years ago, there was a huge series of eruptions here. You can pick out literally hundreds of lava flows over on that wall. Each line delineates the different lava flow. It's over 3,000 feet of overlying flows.
What makes Steens special is that 16 million years ago, when this lava was erupted, the magnetic field was in the middle of a flip. Taking samples from dozens of flows all the way up the mountain, Rob and his colleagues have pieced together a detailed record of this magnetic reversal, although it's so surprising that not everyone accepts it.
What we found as it started to reverse was the strength of the Earth's field decreased dramatically by 80 or 90%.
The field started out pointing south, but as it weakened, the direction of the field began to change erratically. After 300 years, it had swung a full 180 degrees to point north, and the field's strength started to recover.
But it couldn't hold that polarity, and it fell back to reversed, and the intensity crashed again.
Once more, the Earth's magnetic shield practically disappeared, this time for 3,000 years. What was left was changing so fast that Rob found a flow that captured these wild gyrations even as the lava cooled.
And what we found was even harder to believe. The quickly chilled margins in the bottom and the top had one direction, like that of the underlying flow, and the middle portion had a direction that was 60 degrees farther away. It was just as though, while the flow cooled, the field had moved 60 degrees, which if you calculate it out, that comes to about 6 degrees of movement per day. If we were observing this with a compass, you would be able almost to see the motion with your eye. It was truly astonishing and extraordinary.
The lava layers of Steens Mountain suggest we could be in for magnetic chaos, with magnetic north changing from day to day. More seriously, for perhaps thousands of years, the Earth's magnetic shield will be weakened, something that will affect every person on the planet.
The intensity of the magnetic field will be weaker, maybe 10, maybe 100 times weaker than it is today, which means that more cosmic radiation will get through.
This basically opens our defenses so that solar and galactic radiation can hit the atmosphere directly. And this means that the radiation at ground level increases as well.
One estimate is that our overall exposure to cosmic radiation will double, and in some places it could be even worse. Today, the magnetic field focuses space radiation towards the far north and south, where few people live. But as the main field collapses, the weak field that's left will have a more complex structure. Instead of just 2 magnetic poles, there may be 4 or even 8, slowly moving across the Earth's surface.
The structure of the magnetic field won't be the nice, smooth, simple dipole structure that we have today, which tends to deflect charged particles, cosmic radiation, to the poles of the Earth. Instead, there'll be several poles all around the Earth, maybe close to the equator. And so not only will the field be weaker, the field will tend to focus cosmic radiation at low latitudes where most people live.
This unfortunately means more deaths from cancer. It's roughly 15 per million people per year. That is the amount of deaths we're talking about. And if you multiply that over the whole population of the Earth, that becomes a significant number.
It's impossible to know for sure, but the best guess is that every year 100,000 people would die from the increased levels of space radiation. But of course, this would still represent only a relatively small increase in the overall incidence of cancer.
So it's not going to be catastrophic. It'll be something to be concerned about, but it won't be a catastrophic event. And certainly by the time it happens, civilization will have figured out how to deal with it.
The field will come back. In the case of Mars, we know that the field will not come back, and it has been gone for billions of years, so the effect has been very, very serious on the Mars atmosphere. But on the Earth atmosphere, just a few thousand years of no magnetic field are not expected to result in a very large stripping of the atmosphere.
Scientists now know that the magnetic reversal that is inevitably coming will have serious consequences for our descendants, but it won't be a disaster for planet Earth. And as our children's children's children wait for north to become south, they may find that a world without a strong magnetic field has its compensations.
The great thing is that it would be possible to see the aurora just about every night, all over the Earth. So London behind me, for example, we might be able to see great aurora just about every night of the year, shimmering and moving in the sky as the solar wind hits the atmosphere directly, and it glows like a neon light.
Aurora will be very exciting. I can imagine a very interesting dynamic magnetic field outside of the Earth during the next reversal.
I would love to see a reversal happen, but it would involve me living rather longer than I planned to, but that would be very nice. In fact, it's one of the great tragedies of life. We never see how these things work out.
I'd really like to know how it does it and why it does it, and when will it do it again?
Sweet magnetic pull.